Welcome to this session. Today's agenda is to cover recursion and recurrence relations. So primarily we have three sub-agenda points. One is recursive definitions, where we'll be able to recall our fundamental concepts of recursion. We'll be defining sequences, sets, functions, and algorithms in the form of recursion. Then we'll get introduced to recurrence relations, and finally we'll be talking about possible ways of solving a recurrence relation. So let's start with the recursive definition. So if we recall our fundamental concepts of recursion, and at the same time we also recall our fundamental concepts of induction. Induction or recursion are somehow interchangeable. Both of them define the next case based on the previous solution. So, for example, if we recall the fundamental principle of recursion, fundamental principle of induction, which we have been using to prove different claims. So we used to say that if a proposition Pk is true, then based on the truthfulness of this proposition, we used to prove that Pk plus 1 is true. So the truthfulness of the next proposition is primarily dependent on the truthfulness of the previous proposition. And another important component which we have seen so far to complete this principle of induction was the base case. And that was that P naught should also be true. The base case should be true at its first possible value. So this is what we call induction, which means that we define our next proposition or truthfulness of the next proposition based on the truthfulness of previous solutions. And in the form of recursion, if you recall recursion, so in recursion, what we used to say was, so for example, if you recall the recursive definition of factorial function, so a factorial of some number, which we used to notate as n factorial, is defined as n times factorial of the previous integer, which is n minus 1. So this is the recursive definition of the function factorial. And this statement is accompanied by its base case that factorial of the smallest possible non-negative integer, which is 0, factorial of 0 is 1. So we keep on rolling back in terms of our recursive calls, and we land onto the base case that factorial of 0 is treated as 1. So these two statements together define recursion. So let's start with the recursive definition of sequences. So the first example is Fibonacci numbers. So Fn is nth Fibonacci number. The recursive definition is that a Fibonacci number is an integer which is sum of the previous two Fibonacci numbers. So in addition to this recursive definition, what we know is that what is the base case? We know the first two Fibonacci numbers. So the first Fibonacci number is notated as f naught. We call it as 0. That first Fibonacci number is 0. And second Fibonacci number is f1, that is 1. And for all other positive integers greater than 1, we define a Fibonacci number as a sum of the previous two Fibonacci numbers. So now if you look at the first line, that essentially defines the sequence of Fibonacci numbers. First Fibonacci number is 0, then 1, and the sum of first two Fibonacci numbers, sum of these first two base cases is the next Fibonacci number, and sum of the previous two Fibonacci numbers, then for example 1 and 1 get added up to 2. And this principle holds true for all other integers. So for example, if we know these two Fibonacci numbers, by adding these two, we can find the next Fibonacci number, which is 55 in this example. Or mathematically, we can summarize these three lines together, that Fn, nth Fibonacci number is 0 if n is 0, Fn is 1 if n is 1, and in all other cases when n is greater than 1, it is sum of the previous two Fibonacci numbers. If you look at another example, this is another sequence. So if you recall our fundamental concepts of sequences and sums, we used to use this term Tn to notate triangular numbers. So essentially, triangular numbers are the number of balls which we can fit in a perfect triangle. So for example, if we start with an empty triangle that contains 0 balls, if we start with a triangle with 1 ball that contains 1, but if we start increasing size of the triangle, so over here we have in total 3 balls. So if we keep on increasing it further, we have now 6 balls, 1 plus 2 plus 3 is 6. And same way, if we add one more column over here, so 1 plus 2 plus 3 plus 4 is it's 10 is the next triangular number. So the number of balls which can fit in this triangle is essentially the triangular number. So if you look at this visual demonstration of the triangular number, so this triangular number is essentially this is T4, the fourth triangular number. So this is sum of the number of balls which are in the smaller triangle plus the number of balls which we fit in this column. So the number of balls which are in the previous triangle are Tn minus 1 plus the new balls which we have added, the new column which we have added to grow the triangle. So this gives us Tn. So this is the recursive definition of triangular number. By the reason it is recursive is that Tn can be computed using a smaller triangular number. Closed form of a recurrence relation and almost every statement about recursively defined structures are usually proved using induction. So for example, if you look at Fibonacci numbers, so there's a claim that every third number is even. So if you focus on the red integers over here in the first sequence, the first one is 0, then after 2 integers, the next one is even. After 2, skip the 2, then every third is an even integer. So we say this is a property within Fibonacci numbers that every third number is even. So we notate it as F3n. So F3n is the third Fibonacci number where n starts from 0. So our base case is n is 0. So F3n will be 0, and that is 0. That is the first Fibonacci number, which we know from the recursive definition of Fibonacci numbers. We know that F0 is 0. So base case is proven. So we suppose that F3n minus 1 is even, and based on this inductive hypothesis, we are going to build the truthfulness of F3n, that the next third Fibonacci number is also even. So when we say next third Fibonacci number, so F3n is a Fibonacci number which is primarily sum of the previous 2 Fibonacci numbers. So if you try to recall the previous 2 Fibonacci numbers, they are F3n minus 1 plus F3n minus 2. So this is the recursive definition of F3n. So our target is to figure out, we need to expand them further, and we'll keep on expanding until we land onto something which can clearly give us that the resultant is an even number. So let's try to substitute these 2 Fibonacci numbers with smaller ones. So F3n minus 1 is sum of F3n minus 2. Sorry. 2 has to go in the subscript. So F3 minus 2 plus F3n minus 3. So these 2 numbers are essentially representing this number, and we retain the other number as it is. So this is F3n minus 2. Now focus on these 3 different Fibonacci numbers. Where are they coming from, and what do we know about their characteristics? So our inductive hypothesis says that F3n minus 3 is even, which is this number. So this is even. When we say it is even, that means that this number equals 2k. And if we look at the first term and the last term, they are same. So we can write them as 2 times f3n minus 2 plus 2k. So over here we can take 2 as common from here and here. So the resultant is going to be even. So hence f3n is even. The set of natural numbers is what we notate using capital N, and it contains non-negative integers. So we can define sets as in the form of the recursive definition. So we say that the first element is part. This is when we say first element is part of set of natural numbers. That means that we are doing something which is equivalent to base case. And for all numbers, if x is part of n, then x plus 1 is also is part of or member of n. And nothing is an n unless it satisfies 1 and 2. So if you recall the fundamental principle of induction, which is equivalent to recursion, that is that when the first domino falls, that hits the next one. The second hits the third one, and third hits the fourth one, and this sequence goes on. And that's why this third statement is important, that these two are the necessary condition for any particular integer to be part of the set. So nothing is in that set unless it satisfies first and second conditions. If we don't focus on the truthfulness of both of them together, then something like 0.7 can also be part of. If we just try to look at 2, we can assume that 0.7 is part of x as part of our inductive hypothesis, and we'll say that x plus 1 is part of the set. So condition number 3 is necessary, which is essentially n of the first 2 ones. So far what we've talked about is that we've defined sequences recursively, we have defined sets recursively, and now we're defining functions recursively, and that's what we started with this session with the fundamental definition of factorial. So factorial of an integer n means n times n minus 1 times n minus 2 down to 1. So we use this exclamation sign to notate factorial. So any bigger factorial of f of n plus 1 can be computed by computing the factorial of a smaller number times n plus 1. And this definition keeps on applying itself repeatedly until we reach to the base case where we know the factorial. Factorial of 0, which is notated as f0, is 1. So this gives us the final answer. Another example of a function defined recursively is the exponentiation function. So a raised power n is a getting multiplied with itself n times. So we define the exponentiation function or power function recursively. An is 1 when n is 0. Anything raised power 0 is 1. Anything raised power 1 is that number itself. For all larger powers, for all larger values of n, a raised power n is a times a raised power n minus 1, which means that in order to compute a raised power n, we need to know a raised power n minus 1. Or another alternative way of defining the same function is using repeated scaling. So if n is 0, it is 1, anything raised power 0 is 1. If n is odd, we write as that this a times a raised power n minus 1 over 2 times a raised power n minus 1 over 2. And the reason we are writing n minus 1 over 2 is so that we can land into a perfect even power. When n is odd, n minus 1 is perfectly even, so we won't be losing any data in the exponent part. And for all other n's which are even greater than 1, we take a raised power n over 2 times a raised power n over 2. So algebraically, if you look at this expression, this makes a lot of sense because bases are same, we add the powers, we get a raised power n. It's an alternate way of defining exponentiation function using recursion. So we can write this function a mathematical way of writing this function. We can write it as a game. So the algorithm which you can see on the screen is essentially pseudocode of this function where we are computing a raised power n using the first method. And the important part in terms of programming is that this is the recursive call. So this call is equivalent to a times a raised power n minus 1 when n is greater than 1. If it is not greater than 1, then it will be meeting one of the base cases over here. Or we can write the pseudocode for the alternate method of computing repeated squares. So over here, because if you look on the mathematical side, we had two kinds of recursion cases in the first two rows of our mathematical formulation, and that's why in order to translate that in the form of pseudocode or code in a particular language, we'll have to make recursive calls twice or appropriate parameters. Algorithms can be defined recursively. So this is one of the famous searching algorithms which we have talked about previously. And if you recall your CS100 days, you might be able to recall this fundamental searching algorithm, which is essentially searching in a sorted array. So the input is a sorted array of n numbers, and an additional number x has been given. Our task is to return index of x in A if it is present. Otherwise, it should return -1. So the way this algorithm is called binary search. The way it works is, let's have a look on this example, that if we have been given given an array of sorted integers, so our task is look for x. So as part of our first step, what we do is that we find the midpoint of the array. So in this example, 8 is the midpoint. We compare this element against the key, which is notated as x. So if x matches over here, we are done. If it does not match over here, then it will be either smaller or greater than that. So if x is smaller than the midpoint, we confine our search space to the left part of the array. And if it is greater than the midpoint, we confine our space to the right side of the array. So this algorithm will keep on working recursively until we are left with an array of one element. And if that does not match, then we return -1. So let's have a look at the algorithm. So the algorithm, which is notated as binary search, takes three parameters. One is the array itself. It takes st as the starting index, end as the last index, which needs to be considered, and x is the element which we are interested in. So if end is less than st, that means that we have already cut the array into smaller pieces and we are no more left with any element, so we return -1. Otherwise, we compute the midpoint, which is half of n plus start point. So if a of mid is same as x, that is the kind of success situation which we are interested in, and we return that element. We return the index of that element, which is mid index. If a of mid is greater than x, then we confine our search space to the left part of the array. And the last possibility is that we confine our search space to the last part of the array. So I would strongly suggest to try run this on the previous example, which was given over there. Try different values of x and try to comprehend this code, that how it's working. The major benefit which we get over here in binary search as compared to simple linear search is that our number of steps are significantly reduced, which we'll be talking about after a while in this session. So the number of operations or the number of steps which are required to compute the answer by an algorithm is what we call runtime. You will be spending more time on runtime analysis when you get into data structures and algorithms. So we use a formulation which is Tn. This is not the triangular number, but over here Tn is being used to represent number of comparisons being performed by binary search. And Each time we run the function call, some comparisons are performed, and then there is some cost which is associated for recursive call. So the additional number of comparisons which we make over here, in each recursive call are 3, and then we have the no comparisons are if n is less than 1, that means that we have already shrunk to the smallest possible size. So only one comparison is made, which just checks the uh, size of the remaining array. So 3 is the number of comparisons which are being made in every recursive call, and Tn over 2 is the number of comparisons which will be made over half of the array. So we'll be working on this population of the number of steps required by binary search after while. So this formulation is called recurrence. Recurrence is primarily the formulation of number of steps required by a recursive function or recursive algorithm. The recursion is essentially defining a structure. That structure could be set, could be a function, could be an algorithm, could be a sequence in terms of itself. So all of these structures are the discrete structures. Now we are moving to recurrence relations. Recurrence relation is an equation that recursively defines a sequence. So it is useful for modeling and solving many counting problems like Fibonacci sequence. We'll be seeing them in an example that where did sequence of Fibonacci numbers come from. Number of bacteria doubling every hour. We'll be seeing this example. There's another famous example of Tower of Hanoi puzzle. And we'll be finally looking at number of operations performed by a recursive algorithm. And in that case, is binary search. So let's first look at a problem. A young pair of rabbits, one of each gender on an island are there. A pair of rabbits does not breed until they are 2 months old. Each pair of rabbits produces another pair each month, and our assumption over here is that no rabbits ever die. So we are interested in computing number of pairs of rabbits in the island after n months. So this was essentially what we'll see is that this essentially defines Fibonacci numbers. This case was studied originally by a mathematician named Fibonacci. So let's try to put these facts into a table. So each row is essentially is counting number of months. When we are into the first month, we have a young pair, which is less than a young pair of rabbits, which is who are less than 2 months old. So the reproducing pairs are 0 because rabbits will start reproducing when they are 2 months old. So there's only one pair, and there's only one young pair, and that is what is our total number of pairs. In the next month, when we are into month 2, still our number of reproducing pairs are 0, and number of young pairs is 1 because none of them reproduced. So our total number of pairs are still 1. So let me try to put another row into it. So when we get into the third month, so the previous pair, which we had over here for the first 2 months, that is now, when we are into the third month, that is now older than 2 months, and it reproduces. So this pair actually gets over here. This is now part of the group which is reproducing pairs or older rabbits, and it reproduces a new pair. So in the third month, we have a reproducing pair, we have a young pair, and our total number of pairs are 2. When we get to the next month, which is month 4, so in month 4, our number of reproducing pairs are still same. It is still 1 pair because this pair is still young. It has not crossed the age limit of 2 months. So this pair is here. This blue is the same pair as coming from the previous month, and the 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 pair which is older, which is the reproducing pair, that reproduces another pair, and we get two young pairs over here. So number of young pairs is 2, number of reproducing pairs is 1, our total number of pairs is 3. So now the first young pairs becomes the first young pair becomes older, and it joins the club of reproducing pairs, and both of them reproduce. So we have we have 3 young pairs and 2 reproducing pairs. So our total number is 5. So moving forward, if you keep on looking at this thing, with every month, our number of young pairs, reproducing pairs will keep on moving around based on the conditions which we saw, and we will be able to compute total number of pairs. So the total number of pairs over here are essentially representing Fibonacci numbers, which are growing with every month. So in the first 2 months, they were 1, 1, and then the 2 was computed by sum of those 2 pairs. Then 8 is being computed by sum of the previous 2 answers of the total number of pairs in the previous 2 months. So that essentially defines Fibonacci numbers. Another example is Tower of Hanoi puzzle. In this puzzle, we have 3 pegs mounted on a board, 3 vertical pillars, and we have some number of discs, some number of discs which are placed on one of those towers, on one of those pegs, and the given condition is that all of these discs are sorted, which means that the largest disk is at the bottom, the smallest is on top. Number of discs is m, and our task is to move all of them to the last or some other tower over here. We want to move all discs to peg 3, but the condition is that during that entire movement, we have to apply these 2 rules. We can move only 1 disk at a time, and we can never place a larger disk over a smaller one during the intermediate steps. So if you try to pause the video over here and try to play this game with 3 towers given to you. So these 3 towers are there, and try to place 3 disks over here. So we have a bigger disk, we have a medium-sized disk, and we have a small disk. So apply rule 1, rule 2 together, and our task is to move these disks from one tower to the other one. So try to play with 3 disks and try to come up with the analogy, with the sequence of steps which need to be performed. So Tower of Hanoi generally talks about n number of disks, and same algorithm, the kind of intuition which you would have built for 3 disks will be should be generalizable to n disks. The question is, how many moves are required for n disks? So let's try to compute or estimate the number of moves which are required. So this is our initial setting. We have 3 pegs. The first peg is filled with all those disks arranged in the sorted order, such that the bottom one is the largest one in size, and the top one is the smallest one in size. We apply rule 1, rule 2. So if we succeed somehow to transfer top n minus 1 disks from peg 1 to peg 3 using those rules, and that does not mean that we would have done them all in one move. We would have performed multiple intermediate moves, as you would have played in the previous recommendation of playing with 3 disks. So in this setting, from initial configuration to step 1, you can see that top n minus 1 disks have moved to the last peg, and the first peg contains only 1 disk. So the first step is that we need to compute that how many steps we need to spend on transferring top n minus 1 disks from one peg to the last one. Once we have figured out that number, our next step could be that once we were left with this one, and we can move it in one step, we can move it to peg 2. So this is relatively a convenient or easier or trivial step of moving one disk from one tower to an empty tower. That for that purpose, you don't need to look for the rules, because this is the base case, and the tools can be conveniently verified. The last step would be that we need to move n minus 1 disks in some number of steps from peg 3 to peg 2 on top of the largest disk, and that would have completed our task of transferring all disks from peg 1 to peg 2 by applying those rules. So how many total moves have been how many total moves are required over here? So when we say our task was to compute number of moves for n disks, that count is dependent on the number of moves which are required by n minus 1 disks from the top, and then n minus 1 disks as the last step. So that means that the number of steps or number of moves required to move n disk is dependent on the number of moves required to move n minus 1 disk. Okay, so this is the first ICP. So our task is to formulate the recurrence relation. So step 1 takes, we define a function Hn, which represents the number of moves required to get the whole task done for n disks. Hn is dependent on Hn minus 1. Then there is only one move when we have to move the largest disk, and then we have to perform another Hn minus 1 moves. So our total answer is that if we have only one disk to move, then our answer is 1, which is the base case. For the larger value of n, that is dependent on 2Hn minus 1 plus 1. So Hn minus 1 once, Hn minus 1 twice, that gives us 2Hn minus 1 plus the amount of effort which we require from step 2. So sum of these three is this recurrence relation. So this recurrence relation is essentially notating number of moves or number of steps which need to be performed to solve power of an isosome. And this whole exercise and effort is being defined recursively. Let's have a look at another example. So the biological fact is that bacteria double every R. So we are at our R0, so there's only one bacteria, it's unicellular organism. So A naught is 2 raised power 0, which means the number of bacteria which we have at this stage is 2 raised power 0. At R1, it doubles itself. At R2, both of them double themselves. And the growth is now exponential. If you look at the right-hand side in green, you can see the number of bacteria in total. And after every R, so the growth can be noted as an exponential function. So let An be the number of bacteria at Rn. So our task is to write a recurrence relation for An. So every recurrence relation has to have two parts, just like recursion or induction. We need to have a base case, which means that when n is 0, our answer is 1. When n is 1, it means our first R at the start we had one bacteria, and then it starts doubling, which means twice number of bacteria on the previous time step. We are back to binary search. So we have been given an array of size m. Our task is to compute number of operations or number of comparisons required by binary search. So we define this as a recurrence relation. So if our input size, which means if size of the array which is being considered is no more available, we have been cutting the array into pieces repeatedly. So if we are left with n is smaller than 1, then number of steps required or number of comparisons required are 1. And for the larger values of n, number of comparisons are 3 in every function call, plus that function call takes each recursive call runs on an array of size half. So Tn over 2 is the number of steps required to process the array of size n over 2. So Tn over here is essentially representing a recurrence relation notating number of operations required by binary search. There are some properties of recurrence relations. A linear, homogeneous, recurrence relation of order k with constant coefficients is of this form. So over here we are in one sentence we are talking about four properties. One is linear, other one is homogeneous recurrence relation. Third one is its order, and the fourth one is constant coefficient. Which means that in order to compute an, the previous terms starting from n minus 1 to n minus k, they appear as separate terms, and all of them are raised to their first power. When we say the recurrence relation is homogeneous, that means that all terms have the same total degree, so there's no constant term. And the order is the expression for n contains how many previous terms are required to be incorporated in order to compute an. So if you look over here, we are dependent from n minus 1 to n minus k. That means we are interested in, we are dependent on total k previous terms. So its order is k. And by constant coefficients, we mean that each term has a constant over here. And none of those constants are dependent on n. So in the next set of ICPs, what you are supposed to figure out is that whether these ICPs, whether these recurrence relations are fulfilling the given characteristics. If they are linear and homogeneous with constant coefficients, then you also need to additionally compute their order. So what about the first one? If you look at the first one, the first term is power of 2, which is not allowed. So that means the recurrence relation is not linear. If you look at the third one, this is linear, which means none of the terms over here are having any power other than 1. We have constant coefficients. And is the recurrence relation homogeneous? It is homogeneous, and the order is 3, which means that we have to roll back from n minus 1 to n minus 3. What about the one which is given in 5? Is it linear? This is linear. Is it homogeneous? It's not homogeneous because it has the last term is 10, where we have the we might put some arbitrary term over here with raised power 0. What about 13.6? This does not have constant coefficients, which means the coefficients are not dependent. Coefficient is n, but that is dependent on n itself in terms of fn. So what about the last one? It is linear, it is homogeneous, and order is 7. The reason it is 7 is that in order to compute the previous terms, we need to roll back to 7. So that gives us the order of that recurrence relation. So consider the following recurrences and their properties. An is 1, so it has order 0. An minus 1, so this is dependent only on the previous one, so its order is 1. An 2n minus 1 is not homogeneous recurrence relation, because this one is a constant, is a separate term, and its corresponding term has 0 power over here. And for the remaining examples, you can have a look at whether they are homogeneous or linear. The interesting thing is that if you look at all these different formulations, they are representing the same sequence. That means that a recursive sequence may not have a unique recurrence relation. So someone asks you to, given a sequence, someone asks you to find its recurrence relation, you might be adding up into different answers which are equally good. And is the converse true? Is the sequence determined by a recurrence relation unique? The answer is yes, because whenever we look at the recurrence relation, starting from an initial term, given its recursive rules, it must generate a unique sequence. So now we are moving to our last part of our today's discussion, and that is solving recurrence relations. So recurrence relations and initial conditions uniquely determine a sequence. So a sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. And when we say closed form of a recurrence relation, that means that we are interested in computing a form, an answer, or a solution which is not dependent on the previous terms. We need to derive a closed form from a recursive definition which is not dependent on the previous form. So if you look over here at a recurrence relation for a sequence of factorials, so n means n factorial can be computed as factorial of the previous integer times n. And we can, so each recursive call will keep on calling the function on its smaller parameters, and this will keep on calling the same function on the smaller inputs until we reach to the initial term, which is the base case. And then as a result of the completion of that function call, all those calls will start returning the answers which will get plugged in to the places where they were called from, and we'll be able to find the final answer. We can see that number of arithmetic operations, or more specifically multiplications in this expression to compute nth term is n, which means we needed n multiplications to compute 4 factorial. So we'll be looking at two methods to solve a recurrence. So the first method is that we make a calculated guess for a closed form, and in order to see that whether our guess is representing the correct closed form, we'll be proving it by induction. So the question is that where will the calculated guess come from? So usually the calculated guess can be informed by writing first few terms of the given recurrence and try to visualize the sequence. And by looking at the sequence, we might be able to guess its closed form. Or the other method we will be looking at is substitution method. So let's start with the first method first. So this is the recurrence relation representing a number of moves which are required to move n disks in the problem of tower of Nijpelsen. So the first step could be that try to make a calculated guess of the closed form. And one way of doing that is that you can start with a small table. So where in one row you can start writing n, and the other row might be representing hn. So n starts with the base case. When n is 1, so your answer is 1. When n is 2, try to plug in n2 over here. So that means that that is dependent on the previous Fibonacci number, which is 1 in this case. Twice that number plus 1 is 3. So that will come over here. That means that if we have 2 disks, we need 3 moves. So what if we have 3 disks, what will happen? So this number is dependent on the previous number, which is 3 in this case. So 2 3s are 6 plus 1, which means that we can get this whole thing done in 7 moves. And you can verify your strategy that whether you were able to move those 3 disks placed in one peg manually in 7 moves. If not, try to optimize them. And then 4. So 4 2s are 8. 8 plus 1 is 9. So sorry. In order to compute 2hn minus 1, so hn minus 1 was 7, so 2 7s are 14. 14 plus 1 is 15. Did we compute the previous ones correctly? 2 1s, but 2 plus 1 is 3. 2 3s are 6 plus 1 is 7. And same way you can look at 5. So 2 15 are 30 plus 1 is 31. Now you can try to make an informed guess that what kind of numbers are these as we move around, right? So you can see from here that all of these HNs are essentially some powers of 2 minus 1. So this is 2 raised power 2 minus 2 raised power 0 minus 1, 2 raised power 1 minus 1, then 2 raised power 2 minus 1, 2 raised power 5 minus 1, and so on. So our guess is to n minus 1, and now our task is to, in order to verify that, like, will this guess really hold true for the larger values of n? What we can do is that we can do it by induction. Okay, so what is the base case? N is 1. So we need to show the truthfulness for the base case. Then our reductive hypothesis is that pk minus 1 is true, and we have to show truthfulness for pk. Then we use our fundamental principle of induction, and we show that the claim is true. So hence, this is a decent solution that we have landed onto the solution by starting with a heuristic guess. And the guess came from an empirical experiment of writing down the first few terms, observing their pattern, generalizing that pattern, and then proving that thing by induction. And if the guess does not work, then you need to like relook at your guess, maybe like go for a few more terms and tweak the guess, and then again come back to the induction as the proof by induction, just to show that this claim is true. Let's have a look at another example. So this is some recurrence relation, n is being defined in the form of the previous two terms. If n is greater than or equal to 2, the base cases are 0 and 3, when n is 0 and 1. So again, how to make the closed guess? Try to make a table and observe the first few terms. You can pause the video over here, try to make the guess on your own. And if you pause the video and you made a guess on your own, you might have landed onto the solution that Rn is 3n. So your next ICP is that check a few initial terms, that whether this 3n is fine with that, if correct, prove by induction. And you should be able to prove it by induction. Okay, so I would strongly suggest that do this ICP on paper right away while watching the video, and pause the video. But meanwhile, I'm going to solve it. So for the base case, we have two cases. So we need to show the truthfulness for both of them. So when n is 0, so for the base case part, I'm sorry for the poor handwriting. So for base cases, these both of them are the base cases. So we need to show the truthfulness for both of them. So when n is 0, 3n is 0. So our answer is fine. Rn is 0. When n is 1, Rn is 3n, which is 1. So we are fine with that. So the hint over here is that we assume that Rk is 3k, and we need to show, so this is our inductive hypothesis, and our inductive step is that we need to show that how Rk plus 1 is 3 times k plus 1. That's what we want to show. But Rk plus 1 is being defined recursively over here. So that means that this is dependent on 2 times Rn minus 1 is, in this case, is going to be Rk, the previous answer, minus Rn minus 2 is going to be Rk minus 1. So now if you focus on these two terms inside our recursive expression, we can directly bring in this thing Rk, that this is a multiple of 3. What about Rk minus 1? So that is a bit tricky. So that means that in order to use the previous to previous term, we might have to use strong induction over here. So I would strongly suggest that go for strong induction, which advocates that all previous values starting from the base case up till k can all those previous terms are k's can be computed as 3k. So that means that both of these terms are going to be multiple of 3, and that will help us to establish this thing that rk plus 1 can be written in that format. So if you go for strong induction, you should be able to land onto this thing that this is 2 times 3k minus 3 times k minus 3. So this minus will become plus. So if I solve it here, so this becomes 6k minus 3k is 3k minus 3, and this is 3 times, I'm sorry, this is plus 3 times k plus 1. This is what we were supposed to solve. So I have just chalked out in a rough way, but I hope it made some sense. And if not, please stop over here, do it on your own, and you'll have to do it on your own in any case for the sake of ICP as well, which you need to submit online. Okay, this is another example, somewhat very similar. Over here, our base cases are different. So make a closed guess. After observing the first few terms, we made a closed guess, and that is that Rn is 5. So check a few initial terms. If they make sense, prove it by induction. So I will leave it for you, do it on your own. Pause the video over here, solve it by using induction. You might need strong induction again. And the important observation over here is that the recurrence is same, but sequence is significantly different because of the change in the initial conditions. This is another example, again, same recurrence with different base cases. Make a closed guess, pause the video over here, make an informed guess, and observe the first few terms. If you have successfully observed them, you might have landed down to this conclusion that this is an exponential function. Check a few initial terms and see if they're correct. And you will see very soon that the guess is not correct, which means that we have landed onto something which does not hold true. So in other words, we are showing a counterexample where it's not true. If it's not true, then the kind of stuff you do on your own by observing the first few terms is that tweak the guess, recorrect the guess, and then prove the corrected guess by induction so that it correctly represents the closed form of the given recurrence relation. So this is a sequence of triangular numbers. So make a calculated guess for a closed form, prove it by induction. This calculated guess is relatively easy because we spent reasonable amount of time while talking about triangular numbers in our previous discussions. So you should be able to land onto this guess that Kn is n times n plus 1 over 2. And then we can use the same number of steps which we saw while getting introduced to induction, that we can use induction to prove that this is true. Okay, we are now landing on to the last and final part of our today's session. That is that this is an alternative method of solving recurrences using substitution. So if we focus over here on the first part, 2hn minus 1 plus 1. So this is a recurrence relation because hn is dependent on the previous value of the same function, or in other words, hn is dependent on hn minus 1. So we start with this one and we substitute the possible substitution for hn minus 1. So when we substitute the value for hn minus 1, this gives us something like this. So we are now going to substitute something over here. So this gives us 2 times. So the outer 2 remains over there. So we just use this formulation over here. So this gives us 2 times hn minus 2 plus 1. And then we have this previous one as well, which was here, right? So now if you try to summarize this thing, this is 2 raised power 2 hn minus 2 plus 2 plus 1. So if you have successfully grasped the substitution till this moment, you need to do the same thing for hn minus 2. So the rest of the stuff will remain same. So you just need to bring in the possible substitution for hn minus 2 using the given recurrence, and that will be in the terms of hn minus 2. So pause the video over here for a while, try to do it on your own, expand it. If you have put some effort in expanding it, you might have seen that this expression starts evolving like this. So when we have plugged in hn minus 3 over here, we can see that the first power of 2 has started increasing, and also the terms which are getting added up towards tail of the whole summation, they are also increasing in terms of powers of 2. We'll keep on doing this thing repeatedly. So each time we make a substitution, we are going for a smaller value of n. So after some finite number of steps, we should be landing on to n is equal to 1. But when we land on to n is equal to 1, we know the answer that that's going to be 1. So if we keep on opening this expression repeatedly, so we'll be landing on to the place where we have hn minus 1 is, we are landing on h1, whose answer is 1. And when if you look at the previous terms over here, when we were at hn minus 2, our power of 2 was 1. When we were at hn minus 4, our power of 2 was 3. So when we landed over here at 1, that means that we have landed on n minus n plus 1. So our first power of 2 over here is n minus 2. hn1 gets substituted in 1, and we are actually left with sum of powers of 2 from 1 to n minus 1. And this is geometric summation. And you can use the formula of geometric summation, figure out a and r over here, plug them in, and you should be able to land on 2 to the power n minus 1. Let's have a look at another example. So for some given algorithm, Tn is the number of steps which are, it's because the underlying algorithm is a recursive algorithm, so its number of steps are being given as Tn is Tn over 2 plus 5, when n is greater than 1, and otherwise it's 5, which means that some 5 fixed number of steps are being used in every call. So our task is to find the closed form of this expression, of this recurrence relation by substitution. So we start with Tn, and we do the similar kind of stuff which we did previously for tower of an eye puzzle. So we focus on this part. We need to substitute this answer using the recurrence relation. So this whole thing becomes t raised to power n over 2 over 2, which is n over 4, which is essentially n over 2 raised to power 2 plus 5. So this 5 is coming from here, and we have some a previous 5 as well, so that is appended over here. And then we will keep on doing this. So our next substitution will be Tn over 2 raised to power 2 over 2, which will give us 2 raised to power 3 over here. So one new 5 will get added over here. So we'll have 3 5s over here. We'll keep on doing this exercise until we land onto something which is our base case, which is n is equal to 1. When we land onto n is equal to 1, that means that so if you look over here, focus on the parameter which is being passed over here in this recursive formulation. Each time we call it, it gets halved. It is getting divided over 2. So as we keep on dividing it over 2 repeatedly, so very soon we'll be landing onto a smaller input, which will give us 1. So question is that in how many number of steps from n, in how many number of steps we land onto something which is equivalent to T1. So if we succeed to compute the number of steps required from top to bottom while reaching to the base case, then we can substitute this base case with with the answer over here. And another important thing over here is that if you focus on the power of 2 over here in the denominator, that also represents number of 5s getting appended over here. So if we succeed to compute the number of steps which are required to land down to 1, will give us that many 5s getting added up over here. So now for that purpose, you need to recall something from our basic concepts of numeric functions. So for example, if we have our input is 64. So if n is 64, n over 2 is going to be 32. 32 over 2 is going to be 16. 16 over 2 is going to be 8. 8 over 2 is going to be 4. 4 over 2 is going to be 2. 2 over 2 is going to be 1. That's where we need to stop. So the number of cuts which we made over here in our land down to 1 will give us log of that particular number, right? So this is log of 64 is essentially the number of these vertical steps which we have performed with base 2 because we are dividing it over 2. If we change the denominator over here, we'll change the base over here. So this number, the number of steps which are required over here is essentially log base 2 of n, and same number of 5s have been added over here, right? So we'll keep on substituting them over here. So this will give us this thing will come when we say n over 2 to the power log n. That means that will take us to 1. So that will give us t of 1 is 5. 5 plus 5 times log of n will give us the closed form of this particular recursive relation. Let's have a look on a very similar example. Over here, there are small changes where instead of like adding a constant coefficient over here, we are adding n. So we started with Tn, we keep on dividing it again and again repeatedly. So if you open it up, so we'll see that after log n steps, because log n is going to compute the number of vertical steps which will land us from n to 1. So n has been added log n times, which will give us n times log n, and 2 has been multiplied with itself log n times. So this whole expression will evolve into 2 to the power log n. 2 to the power log n is n, and that will give us the closed form of the whole expression. The last example is somewhat similar track. We start with 4tNO2 plus 3n, and now there are two parts. One is the summation part, and I would so the critical point is common, which means the number of vertical steps which take us down to 1 is log n, and expand this expression on your own using the substitution method. You should be able to land onto the answer over here. If you succeed to do that, that would be great. And otherwise, you can have a look at the solution. So that's it for today. So we're done with recursive relations and recursive formulations of sequences, sums, sets, and functions. So we'll be having some recitation session, or might be some like interactive session if you have been having any questions. Thank you very much. That's it for today.